This is the third of 3 lessons on the gyromagnetic compass. Previously, we have established the need for the gyromagnetic compass, and we showed the basic components which make up the system. We also showed how the detector unit, or flux valve, senses the Earth's magnetic field and reproduces it within the compass indicator. We are now going to examine some of the components more closely and also add some new ones. The first one to look at in more detail is the compass indicator dial. Here is a typical modern compass indicator dial. As we know, the compass card is directly driven by the shaft from the gyro. It rotates as heading changes, and the heading is read against the index line in the 12 o'clock position, which is sometimes called the lubber line. A desired heading can be selected by the pilot by rotating the heading selector control. The heading select marker, usually called a bug, indicates the selected heading. If the magnetic input from the flux valve fails, a warning is given in the form of a heading warning flag. Depending on the level of sophistication of the particular model, there may well be other facilities and warnings, particularly if it is a modern horizontal situation indicator, or HSI, which is also used to display VOR and ILS information. However, these will be covered in radio navigation and are not discussed further here. If the magnetic input from the flux valve should fail, or if it becomes unreliable due to proximity to one of the Earth's magnetic poles, it is possible to operate the gyromagnetic compass in gyro mode only. If this happens, it acts as a DGI and will need to be reset periodically to a directional reference, such as a standby compass or other source of aircraft heading. When it operates as a DGI, this is referred to as free mode, whilst its normal magnetically monitored operation is referred to as slaved mode. This is a typical modern compass controller. With the free/slave switch at slave, the compass operates in the normal magnetically monitored mode. If the switch is moved to free, the magnetic signal from the flux valve is disconnected, rotor-stator comparison ceases, and the gyro is no longer tied in azimuth, and so acts as a free gyro, exactly like a DGI. When it is being used in free mode, the pilot adjusts the indicated heading in order to correct it to an external datum heading with a switch, which is spring-loaded to the central position. During normal flight in slave mode, there is usually continuous slight motion due to oscillations of heading and to vibration, which means that rotor-stator comparison of the magnetic flux valve signal against the gyro shaft position continuously generates very small error signals. The error signal, and therefore the precession amplifier, are continuously hunting. This is normal and is how the system is designed to work. These error signals pass through a voltmeter called an annunciator on their way from the amplifier to the precession motor. The annunciator looks like this. Normal operation results in continuous slight oscillation of the vertical line about the central position. The annunciator is useful to the pilot for 2 main reasons. It is an indication that magnetic monitoring of the gyro is taking place. It shows that the compass is synchronized. And on systems where it is necessary for the pilot to synchronize manually on startup, or after a desynchronization, it indicates which way to turn the compass. Gyro wander can take 2 forms: drift and topple. The tendency to drift is overcome, as already described, by slaving the gyro to the flux valve output, thereby making it a tied gyro in azimuth. However, the gyro would still topple over a period of time unless prevented from doing so. It therefore needs to be tied either to the aircraft yaw axis or to gravity in order to keep it erect. Both the yaw axis and the vertical, as defined by gravity, have been used as the datum in various models of compass. Both systems use a levelling switch and a torque motor. To tie the gyro to the yaw axis, the inner and outer gimbals are maintained at 90 degrees to each other by a system of commutators, insulating strips, and brushes. If the gyro topples, the brushes are no longer in contact with the insulating strip, so a current passes through the commutators. Alternatively, to tie the gyro to the vertical, mercury gravity switches are used. Either way, the correcting signals are passed to a torque motor, which applies a rotational force to the gyro in the yaw axis. The resulting precession causes the gyro to return to the horizontal, but at a slow precession rate, so that it does not react wildly to temporary departures from the horizontal, such as turns, accelerations, climbs, and descents. One of the advantages of the gyromagnetic compass over the simple direct reading compass is the facility to electrically transmit heading information to use as an input into other instruments such as the RMI, autopilot, and flight data recorder. The information is picked off from the drive shaft between the gyro and the compass card. The transmitting and receiving device is called a self-syn unit. The word self-syn is short for self-synchronization. A second rotor and set of stators is inserted into the direct drive shaft between the gyro and the compass indicator dial. This is the transmitter unit of the self-syn unit, and is nothing to do with part of the flux valve transmission to the drive shaft. The orientation of the self-syn unit rotor is therefore the heading which is to be transmitted. The rotor is supplied with a constant primary excitation AC voltage, which induces a field in the stators. The stators are directly connected by 3-strand wire to the 3 stator arms of the repeater, so an identical field is reproduced there. As many receivers as are required can be attached. If the rotor of the repeater is not perpendicular to the field in the repeater stators, an AC voltage will be induced in this repeater rotor. This is passed to an amplifier and then to a motor to turn a shaft on which the repeater rotor is mounted. The repeater shaft will turn until no further voltage is detected. The repeater shaft therefore follows any heading changes in the main gyro drive shaft. The receiver shafts are 90 degrees out of phase with the transmitter because the transmitter field is induced in line with its rotor, but the receiver rotors adopt the null position. However, this is easily solved by offsetting the indicator dials by the required amount. Let's summarize this lesson. Compass indicator dials vary with the vintage and the sophistication of the compass, but most have a rotating compass card with the heading indicated by the lubber line index at the 12 o'clock position. Additionally, they all have, in some form or other, a heading selector, a heading bug, and a warning flag if the magnetic input fails. If the magnetic input from the flux valve should fail, or if it becomes unreliable due to proximity to one of the Earth's magnetic poles, it is possible to operate the gyromagnetic compass in gyro mode only. This is known as the free mode. It is operating as a DGI. The pilot must then adjust the indicated heading periodically in order to correct it to an external datum heading. The annunciator tells the pilot that the compass is synchronized. And on systems where it is necessary for the pilot to synchronize manually on startup, or after a desynchronization, it indicates which way to turn the compass. In order to prevent topple, the gyro needs to be tied to the aircraft yaw axis, or to gravity in order to keep it erect. The gyromagnetic compass can be used to transmit heading information to other instruments. This is done by a cell-SIN unit, in which the transmitter is a stator-rotor combination, with the rotor on the compass indicator driveshaft. The receiver or receivers are another stator and rotor combination, in conjunction with an amplifier and an electric motor. This completes all the lessons on the gyromagnetic compass.